Good evening, ladies and gentlemen. Welcome to today's webinar organized by HKIE Civil Division and the Hong Kong Polytechnic University. Today, we are very glad to have Dr. Alfred Wu from the Hong Kong Polytechnic University to share with us on the topic of Hong Kong marine deposit improved by prefabricated band drains and reinforcement. Dr. Alfred Wu obtained his Bachelor of Engineering in Civil Engineering from Hua Zhong University of Science and Technology and PhD in Geotechnical Engineering from the Hong Kong Polytechnic University. He won the Best PhD Thesis PolyU Award offered by the HKIE. His research interests include physical and numerical modeling of marine deposits, ground improvement techniques on soft soils, geosynthesis, application of optical sensing technologies in geotechnical engineering, as well as field experiments on land reclamations. Without further ado, may I now invite Dr. Alfred Wu to share with us on his presentation. Dr. Wu, please.
Thank you, Henry. And thank you so much for Hong Kong IE Civil Division and also the Department of Civil and Environmental Engineering to provide me this opportunity to give this webinar about my research. So before we start today's webinar, please give me a few minutes to introduce our department, CE at the Hong Kong Polytechnic University. As you can see here, so CE at Hong Kong Polytechnic University have gained global recognitions. So we have 26 CE scholars ranked world's top 2 scientists, and we also have many research fellows. For example, we have the members of the Chinese Academy of Sciences. We also have 7 Changjiang scholars, and we have 1 fellows of the Australian Academy of Engineering and Technology, and 1 fellows from the Royal Academy of Engineering, UK. So our department has done very well in the recent years in securing research fundings. For example, here we have some major research fund, which is called Theme-Based Research Scheme. Apart from that, we also secured funding such as Green Tech Fund and Lentil Conservation Fund. And we also have very good collaborative research funds with other teams, and also we have some major research impact funds focusing on different areas in civil and environmental engineering. So in our department, we offer civil engineering and also environmental engineering and sustainable development degree for undergraduate students. And we also have master degree for civil engineering and environmental management and engineering. So here we have our outstanding alumni. So some of you may recognize our outstanding alumni. And in our department, we have excellent facilities. So you can see here, we have 30 laboratories and 2 workshops and 1 research center in Shenzhen. And here are some information about our department. So if you are interested in, so you can scan this QR code or visit our website. And here we also have the social media channels for our department. Okay, so now let's start today's webinar. So today I'm going to present the research I did during my PhD study and also during my postdoc period. So the research is about the Hong Kong marine deposit improved by prefabricated band drains and reinforcement. So here are the contents. So first of all, I will introduce the background, and then I'll talk about Hong Kong marine deposit, and then followed by the 2 main parts of today's webinar, which is the Hong Kong marine deposit improved by the prefabricated band drain and Hong Kong marine deposit improved by deep cement mixing method. So as we know, Hong Kong has a long history of land reclamation. So we can see from this picture, shows you the reclaimed land since 1841. 70% of Hong Kong's land area was created through the land reclamation. Let me see this chat in the, oh, sorry. And for land reclamation and some other nearshore or offshore development often need to deal with soft marine soils. Soft marine soils normally refer to the clay or silty soils with no undrenched shear strength and high compressibility. So leaving this kind of soil in place would result in a large settlement or even unacceptable post-construction differential settlement. So here you can see this is a typical seabed soil profile in the Hong Kong Sea area. So on the top, we have the upper marine clay and followed by alluvial and a lower marine clay and so on. So those marine soils are actually quaternary sediments formed during the Holocene or pre-Holocene period. So in today's webinar, we are mainly focused on the upper marine clay, which we also call it Hong Kong marine deposit. So here I summarize some basic properties of the marine soils in Hong Kong's seabed. So for example, we can see the upper marine clay is classified as highly plasticity clay. And for the upper alluvium, it's classified as medium plasticity clay. And for the lower marine clay, it's classified as medium to high plasticity clay. And then below the marine clay, it's lower alluvium, which is basically sand. And below that is CDG and the bedrock. So here we can see some basic properties of Hong Kong marine deposit, HKMD. So for the HKMD, the clay content may vary from 5 to 70%. The clay content refers to the particle whose size is smaller than 2 micromillimeters. So as we can see here, the friction angle of the Hong Kong marine clay actually decreases with increasing the clay content. And also here, so we can see the major minerals of Hong Kong marine deposit and major chemical composition of HKMD. So HKMD is kind of problematic soil. It has high compressibility. So the compression index or compression ratio is from 0.3 to 0.5. HKMD is also of high plasticity, high sensitivity, and most importantly, has high degree of creep or secondary compression. So you can see here, those are some data to show you the creep coefficient of HKMD. So the creep coefficient of Hong Kong marine deposits range between 0.24% to 2.5%. So if we compare the creep index to the soil around the world, so we can see the range of the creep of HKMD actually is similar to some organic soil. So it's just a little bit better than peat. Okay, so now we need to talk about the creep or secondary compression. So creep is we call continuing deformation or viscous compression under the constant effective stress. So how do we measure or how do we test the creep or secondary compression? So usually we do a so-called odometer test, so which is also a consolidation test. So we put a soil sample on this odometer apparatus, and then we apply pressure on top of the soil. And on the top and the bottom layer of the soil, so we can let the water drain out. So with the time, we can measure the settlement or compression of the soil, and then we plot the measured settlement, or we can also convert the settlement to the void ratio of the soil, and then we plot the void ratio versus time, and this is a typical consolidation curve of a soil. So as you can see here, at the first part of this curve, so the first part is, we call it primary consolidation. So during the primary consolidation, the effective stress increases. And at the point which is showing here end of primary consolidation, TEOP. From this point, the excess portal pressure will not change, which means that the effective stress is going to be constant after that. And we still have the deformation or the change in void ratio. So this change in void ratio or deformation is called creep. The possible mechanism of soil creep can be explained by first, the viscous deformation of clay skeleton, and second, the viscous deformation of clay plates, and third, the viscous absorbed water. So those are three possible mechanisms to cause soil creep. And if the soil has a significant creep behavior or high compressibility, so it actually will create some problems for the engineering. So for example, so it will induce long-term settlement, especially for the post-construction settlement, and sometimes it may also occur, induce differential settlement. So for example, on the left-hand side, this is the measured data from the famous Kansai International Airport. So this airport is built on the artificial island. So as you can see here, the top part actually tells you the loading applied on the seabed. So as we can see, by the end of 1990s, the construction is almost finished. But as you can see in this figure, the settlements keep going until even now in 2024, the settlement is still ongoing. So this is recorded. It has a large post-construction settlement. And in the right-hand side, so we can see two pictures in Hong Kong. So the first one is the differential settlement happened in Ma'anshan in 2002. And the second picture actually shows you the differential settlement near the exhibition center station in 2017. And the soil creep and high compressibility can also create other problems. So for example, it may influence the effects between the soil and the structural interaction. And also sometimes we may need to consider the effects of soil creep and settlement on the negative skin frictions. So for example, here we have a board pile in a recent reclaimed soft soil. So if the soil has significant creep or significant settlement, it will generate the so-called negative skin friction to the pile. So this negative skin friction may consider as part of additional load to this pile. Okay, then how can we estimate, or how can we calculate the settlement of the soil if we are considering the soil creep? So there are three methods if we are considering the settlement with creep. So the first method, we call it fully coupled consolidation analysis. As we all know, as we all learned from the basic soil mechanics, so Teizaki proposed the consolidation analysis theory, but in his theory, he didn't consider the soil creep. So in this case, the Teizaki theory is not very good to predict the settlement, especially long-term settlement. So in this case, so we try to use a fully coupled consolidation analysis, which we coupled the consolidation theory with Yin and Graham's 1D elastic viscoplastic model. And the second method, we can use final element analysis. For example, in a commercial software Plaxis, we have a model called soft soil creep model. So this model can consider soil creep. And the third method is, we call it a simplified hypothesis B method. So this method and also this EVP model was developed by my PhD supervisor, Professor J.H. Yin. And Professor Yin's simplified hypothesis B method has been adopted in the Canadian Foundation Engineering manuals. So if you are interested in this method, so you can find this Canadian Foundation Engineering manual. So there's detailed steps to show you how we use this method to do the settlement calculation. Okay, so now we know soil creep is kind of a problem we need to face. And how do we handle this kind of problem? So how do we handle the HKMD with soil creep? So in Hong Kong, we actually had two methods. The first method is dredged method, which means we dredge the HKMD away from the seabed and we replace this soil with competent soil. So in this case, we can avoid the problem. And the second method is to use ground improvement method. So in Hong Kong, we have tried a vertical drains plus surcharge method. So this method, we will talk about this a little bit later. And apart from that, we can also install stone columns, sand compaction piles. Recently, the deep cement mixing method have been introduced to Hong Kong to form either column, type, or blocks to strengthen or reinforce the HKMD. So in today's webinar, we call those columns as inclusions or reinforcement for HKMD. Okay, now let's talk about the first method to improve HKMD, which is we improve it by prefabricated band drains. So if the prefabricated band drain is installed in a vertical direction, so in this case, we call it prefabricated vertical drain. So this prefabricated vertical drain, PVD, have been used in Hong Kong since 1980s to accelerate the consolidation process. So in this slide, I summarized some project which this PVD has been used. So for example, there was a test embankment at Choi Lai Kok to try the vertical drains and surcharge method. So usually the vertical drain is used with surcharge preloading. So the advantage of this ground improvement technique, or the principle of this ground improvement technique, is to make soil over-consolidated. And in this case, we can reduce the post-construction settlement and the creep settlement. So here we have a figure to show you the principle of this method. So first, for example, if we want to build the buildings, so let's say the loading is from point A to point B. So this is design loading. So as we can see from this figure, so the settlement of the soil due to this construction will be SB minus SA. So this is the settlement of this design loading. So you can see here the settlement is quite big. So if we do the if we do the surcharge preloading to, for example, point E, and then after some time we remove this loading to the original stress place, for example, point D, and then we start to do the construction from this point, and then you can see for the same design loading, so the stress point moved from D to C, and the settlement induced is SC minus SD. So you can see compared to the previous settlement, after preloading, the settlement is much smaller. And also if we compare the creep rate at point B and point C, so we can find that the creep at point C is much smaller than the creep at point B. So that's why we say if we can make the soil over-consolidated, we can reduce both construction settlement and the creep settlement. And this preloading method can be also achieved by applying vacuum pressure. Okay, so recently at PolyU, Professor Yin proposed a sustainable land reclamation approach and a combined ground improvement method. So in this method, we use the dredged HKMD as fill material from the land reclamation. And we use the prefabricated horizontal drains, PHDs, plus vacuum preloading for preliminary treatment. And after the preliminary treatment, we installed PVD, prefabricated vertical drain, plus vacuum or surcharge loading for further treatment. So here shows you the stages of this land reclamation approach and the ground improvement method. So the first stage is to build the seawall. And in the second stage, we will install the first layer of horizontal drains and start to fill the HKMD. And in the next stage, we try to install another layer of horizontal drain and keep filling the HKMD. And in the stage 4, so this represents that we finish all the filling stage, and we start to apply vacuum to the horizontal drains. And after some time, so this we call preliminary treatment is finished. And at the top of the filled soil, there will be a crust layer with high bearing capacity. So in this case, we can try to install vertical drains by using heavy machine to install the vertical drain to the filled Hong Kong marine deposit and also the existing Hong Kong marine deposit and treat them together. And for this secondary treatment or further treatment, we can use either vacuum preloading or we can also use the surcharge preloading. So we have done some small-scale laboratory experiments at the PolyU to demonstrate the feasibility of the proposed ground improvement method. So for example, here you can see here, this is a 2D cylindrical model. So this physical model was done by my colleague, Dr. Low. So in this model, the HKMD slurry was filled in this cylinder model. And we used, at the bottom of this cylinder model, we installed a horizontal drain, and then we applied the vacuum to the horizontal drain. So this is step 1. And in step 2, we installed a PVD vertical drain inside the soil, and then we applied vacuum to the horizontal drain and the vertical drain together. And in the step 3, so we keep the PHT and PVD together, and also we apply the vacuum or surcharge loading. So here is a video to show you the effect of the horizontal drain plus the vacuum. So we can see that the PHT and the vacuum method actually can can accelerate this consolidation process in a very fast way. And here we draw the vacuum pressure distribution for this model test. And at the bottom of this slide, so you can see the average water content of the Hong Kong marine slurry after each stage. So the initial water content of the HKMD slurry was 350%. And after first step, so after PHT plus vacuum, the water content reduced to 150%. And after we installed PVD, so the water content further reduced. And after applying the surcharge, so we get the final water content around 46%. And we had done another small-scale laboratory test. So this is a 2D plane strain model done by my colleague, Dr. Pan. So this model was conducted in a rectangular model. So you can see here we have the rectangular model. And at one side of the model, we have the FRP pipe pipes to simulate the seawall. And inside this area, a layer of PHT grid were installed and also some transducers. So for this physical model test, we also have 4 steps. So in the first steps, we install the horizontal drains and then start to fill a layer of HKMD. And in the second step, we start to install the second layer of HKMD and fill with another layer of HKMD. So in this case, the second layer of HKMD can serve as a surcharge loading to the previous filled HKMD. And in the step 3, we install another layer of another layer of PHT and another layer of HKMD. And in the step 4, we installed PVD. So these are the 4 steps for this model test. So as we can see, the average water content also had significant drop after the treatment. And here we shows the result of these two model tests. So in terms of undrained shear strength, so as we can see at the beginning, so this soil, HKMD slurry, has almost zero undrained shear strength. And after the treatment, so for the first physical model test, we got the undrained shear strength almost 40 kPa. And for the second model test, we also have the undrained shear strength more than 30 kPa. And apart from the laboratory tests, we also did a field trial at the Tongchong Newtown extension site. So this field trial was a joint effort of CEDD, PolyU, AECOM, BuildKim, and Samsung CNT. So in this field trial, we tried to test the stage 2 to 4, which is a preliminary treatment of Hong Kong marine deposits using horizontal drains and vacuum preloading. Okay, so in this field trial, the initial water content of HKMD slurry was 180%. And here we have some basic properties of the HKMD used in this field trial. And also we used a drain, a prefabricated drain from the Korean company as vertical drain to improve the HKMD. And here shows the layout of this field trial testing pit. So this testing pit has the base size of 12 meter times 8 meter and a depth of 3.5 meters. So we also installed a number of transducers to measure, for example, water pressure, settlement, or effective stress in the soil. And here shows you the instrumentations and also the horizontal drains and HKMD fields. So in this field trial, the vertical spacing of the horizontal drain is 0.5 meter, and the vertical spacing of the vertical drain is 0.8 meter. And here are some pictures taken during the field trial. As you can see at the beginning, so this is how the field trial pit was formed, and just near the trial pit, we have a mixing pit to prepare the HKMD slurry. And the second stage, we build the access platform. So later we can use this access platform to take some soil sample for laboratory testing. And in the third figure, we start to install the transducers and try to install the horizontal drains. And this picture shows how we prepare the Hong Kong marine deposit slurry. And picture E shows the first stage when we finish the filling of Hong Kong marine deposit, and you can see some some horizontal drains placed on the bottom of the testing pit. And figure F is the picture we took after finishing the filling process. And this slide shows you the time record of soil filling and the vacuum applications. So as you can see, the filling process started from December of 2021, and the application of vacuum started from March 2022. So in total, we have around 4 months time to treat or improve this HKMD. So here we show you some data we measured during the field trials. So if we plot the settlement in Osaka method, and then we can try to find the ultimate settlement, which is around 0.238. And then in this case, we can calculate the average degree of consolidation after the treatment, which is around 96%. And this slide shows you the measured water pressure data and also the average water pressure profiles during the field trial. So by using this for the pressure profiles, we can also estimate the average degree of consolidation. So here our result is around 78%, which is slightly smaller than the degree of consolidation we estimated from the settlement data. And here you can see the final result after 4 months treatment. So for example, for the undrained shear strength profile. So at the beginning, we have very low shear strength. And after 4 months treatment, so we can see that about below 5 meter level. So we can see that the undrained shear strength generally increase with the depth. And about 5.0 meter level. So this part, so which we call it cross layer. So we absorb formation of cross layer. So this cross layer has high undrained shear strength, and this is due to the combined effect of the vacuum preloading and also the drying effect on the surface. And if we look at the water content profiles, so the first picture, picture A, shows the water content during the treatment. So we can see there's significant drop at each time we measure the water content. And figure B shows the comparison between the initial water content and the water content after the treatment. So here, the liquid limit of Hong Kong marine clay deposit used in this field trial was 48%. As we can see, after 4 months treatment, the water content reduced from 150% to around or even below the liquid limit. So here actually demonstrate the feasibility or the effectiveness of this proposed ground improvement method. And also we are thinking about how to design the horizontal drains. So basically, the design parameters are the spacing of the horizontal drains. So the spacing of the horizontal drain can be determined based on the required treatment duration and the required degree of consolidation. So normally, the horizontal drains are treated in 2 ways. We try to do analysis. The first way is to treat to consider the horizontal drain as a square pattern. And in this case, we can use the axisymmetric solution to calculate the degree of consolidation. And the second method is to treat the horizontal drain or convert horizontal drain into a sheet pattern. So in this case, we try to apply the plane strain solution to calculate the degree of consolidation. So here, my colleague, Dr. Chen, he proposed a mapping method. So this mapping method actually combines these 2 patterns, the square patterns and the sheet patterns together, and then proposed a generalized equation to calculate the degree of consolidation. And here is the equation. And also we have a generalized time factor and a generalized correction factors. So by using this mapping method, so we can plot this figure to show the relationship between the normalized spacing and also the normalized time and 90% of degree of consolidation. So the normalized spacing is the spacing normalized by the spacing of the horizontal drain used in the field trial. So those spacing are normalized by 0.5 for horizontal spacing and 0.8 for vertical spacing. Okay, as we can see from the results, so we can draw the conclusion that reducing the vertical spacing is more effective than reducing the horizontal spacing in enhancing the performance of vertical drain in this field trial. Here are some more pictures to show you this field trial. For example, the first picture shows you the initial surface of this HKMD slurry. And after treatment, so as you can see, so the soil is turned from a slurry to a relatively strong ground, and people can stand on the ground, and also some lightweight machine can be accessed to the treated soil. Okay, and now let's move to the second part of today's webinar, so which is Hong Kong marine deposits improved by DCM deep cement mixing method. So this deep cement mixing method, DCM, is actually very special because it was first used in Hong Kong for the construction of third runway system of the Hong Kong International Airport. So the third runway system was built on a piece of the seabed, of which approximately 40% of the seabed was contaminated. So in this case, the deep cement mixing method was proposed to treat this contaminated soil. So at that time, so this method, DCM method, was new to Hong Kong, and we don't have local standard available at that time. So in this slide shows you the layout or the design of DCM for the reclamation. So the first step is to build a layer of sand blanket on top of the contaminated soil. And after that, we try to install DCM. And then if DCM gain enough strength, and then we start to install the geotextile reinforcement, and we start to fill the fill material and do the surcharge. So in the main reclamation area, DCM was installed in the form of columns, and the load transfer platform was designed with a synthetic reinforcement. So in 2016, when I just started my PhD study, so I was thinking these three questions. The first one is, what is the stress strain behavior of the HKMD stabilized by cement, or in other words, DCM? So there are many data and standards in other countries, but at that time, we have limited experience in Hong Kong. And the second question is how to consider the load transfer between the DCM and surrounding soils. There are also many existing methods to estimate load transfer, but we don't know which one is most suitable for our case. And third question is, how is the soil creep influenced by DCM? Luckily, in 2023, there's a GEO report published to actually in this report, it tells us a standard method to test the unconfined compressive strength of cement stabilized the soils. But as I mentioned before, in 2016, so we don't have much experience regarding in testing. So therefore, from since 2016, me and my colleague, for example, Dr. Ho, Dr. Chen, and some FYP students, we start to conduct laboratory testing of DCM. So this slide shows you some preparation procedure of how we prepare the DCM samples in the laboratory condition. And after curing, so we need to check the flatness of the upper and the lower surface of the column, and we do the unconfined compression test to the DCM specimen. And here is the standard setup at PolyU soil lab to test the DCM columns. And here, from our experiment result, we draw this correlation between the unconfined compressive strength of the DCM and also with the water cement ratio. So as you can see here, we also compared our correlation with different soil in other countries, for example, Singapore clay, Bangkok clay, and the Japanese clay. So from this figure, we can see that the Hong Kong marine clay, after stabilizing by cement, is actually behavior better than Singapore and Bangkok clay, but not as good as Japan Arica clay. But here, I want to mention that the laboratory testing result is quite different from the field testing results. Okay, so this is the one thing we need to pay attention to. And also we summarize some failure mode of the DCM columns. For example, we have shear fracture, we have cone split fracture, we have columnar fracture. So these failure modes are somehow related to the cement water ratio. And after knowing the some basic understanding of the stress strain behavior of DCM, we start to design the laboratory tests like physical model tests to investigate load transfer. So for example, here shows the layout of this experiment. So in this experiment, we have DCM column, we have HKMD, and also we have sand and geotextile. So here are the particle size distribution of HKMD, so which was collected from coastal area of Lantau Island, and also we have the river sand, which was from Guangdong province. And here shows some testing results of the DCM columns. And here for the geotextile, so we use the FBG sensor to measure the tensile strain. So FBG sensor is similar to the strain gauge, but instead of measuring the electrical signal, so we measure the optical signal. So we measure the wavelengths of the FBG sensor. So this wavelength is sensitive to strain and temperature. So by measuring the wavelength change, we can know the strain change in the geotextile. And here shows the procedure of this laboratory test. And here are the testing data for the settlement and excess portal pressure. So in order to investigate load transfer and arcing effect, we have to divide our model into different zones. For example, we have column zone, which is the area of the DCM column and the soil above the column. And also we have the strip zone, which is the area between two column zone. And we have the swell zone, which is the area enclosed by foam strip zones. So after defining these different zones, so we can compare the vertical stress in different zones. For example, in the left-hand side, we can see the vertical stress in the column zone. So it's much higher than applied loading. So this is mainly due to the stress concentration. So the stress tends to concentrate on the DCM column. And if we compare the vertical stress in swell zone and the strip zone, so as we can see, the stress in strip zone are higher or greater than stress in swell zone. And the stress in swell zone is smaller than applied loading. So in this case, we can simply draw the conclusion that vertical stress on the HKMD is reduced due to the load transfer. Okay, so now we can see some more detail about the load transfer. If we plot the vertical stress in column zone and the vertical stress in swell zone, so we can see that if we increase the load, so due to the partially undrained condition during the loading stage, both vertical stress in column zone and the swell zone increase. However, if the consolidation happened, so you can see that here, the vertical stress in swell zone decrease and the vertical stress in column zone decrease. This indicates that the vertical stress in swell zone is transferred to the vertical stress in column zone. And this pattern can be also seen from the swell zone to the column zone. So in this case, so we can summarize the load transform pattern as the loading in the swell zone is transferred to the swell zone, transferred to the strip zone first, and then the strip zone transfer the loading to the column zone. And on the other hand, so we can define three load parts, so which are load part A, B, and C. So for load part A, is the loading transfer directly to the column, and load part B is the loading transfer through the geotextile to the column, and load part C is the load carried by the soft soil. And after calculating the load part, so we can also try to calculate two factors. So one is called efficacy, and the other one is called stress reduction ratio. So the efficacy actually tells us the proportion of the load taken by column, and the stress reduction ratio tells us the effect of geotextile and reducing the vertical stress on the subsoil. And here, as we mentioned before, there are many existing methods to quantify the load transfer. So here we select the 4 major design guidelines and to compare the result with our testing result. So as you can see here, for efficacy, so it decreased during the process of increasing the surcharge loading, but it increases during the consolidation of the subsoil. And the efficacy after consolidation slightly increased with the increase of surcharge loading. And if we compared our data with the existing method, so we can see that the CA model, the concentric arch model, and adopted Teizaki method give a good prediction of efficacy. And similarly, for the stress reduction ratio, so it decreases during the consolidation of subsoil. And this stress reduction ratio tends to decrease with the increase of surcharge loading. And adopted Teizaki method can capture general decreasing trend of the stress reduction ratio. And here we show you the effect of the load transfer. So as you can see, the red line is actually the settlement and vertical stress relationship of the Hong Kong marine deposit treated by DCM column. And the blue lines represents the Hong Kong marine deposit without DCM column. So as we can see that the overall behavior of Hong Kong marine deposit improved by the DCM is similar to the over-consolidated soil. So we can also conclude that the load transfer can reduce the settlement of the Hong Kong marine clay by somehow unloading effect to the marine clay. And we also compared tensile stress of the in the geotextile with the calculated the value from the current design method. And then after that, we also did numerical simulations. So for the Hong Kong marine clay, because we need to consider the creep effects. So that's why we use a soft soil creep model. So in this model, we can consider the creep deformation of the soil. So the creep deformation is related to the creep index and also the reference time. And this soft soil creep model in Plaxis is almost identical to Yin and Graham's elastic viscous plastic model in 1D condition. And here you can see the numerical simulation results. So in general, it have good agreement with the measured data. And based on this, here, so you can see the tensile force in the geotextile. And also we try to visualize the arching. So we can see here, after consolidation, the arching is actually quite similar to the arching proposed by CA model, and explain why CA model give a better result in the efficacy. And after this, we conduct a parametric study, try to investigate the influence of different parameters, and then we evaluate those influences by define a degree of influence, eta. So if the eta is greater than 30%, we consider as a medium influence. If it's greater than 60%, we consider as a high influences. So for those have medium or high influences, so we consider whether these factors will have positive or negative effect to the settlement of or load transfer. So here are the results. So as we can see here, so the area replacement ratio, which means the size of the DCM column, actually has very big impact to the settlement and the efficacy. And before it was all about laboratory condition, and how about in engineering scale? Okay, so we use the same final element model, and we try to scale up. And here, so this is the basic information similar to the case in the third runway project of Hong Kong International Airport. So in this simulation, so the air replacement ratio of DCM is set to be 20%. And here are the parameters we use for the simulation. But here, those data are not real data for the third runway construction of the Hong Kong International Airport. So which means our result cannot be directly used to explain what's going on in the Hong Kong International Airport. And here we did 4 simulations. So the first one is the simulation with DCM column with considering soil creep. And the second one is a simulation with DCM, but without considering soil creep. And the third one is a simulation without DCM, but consider the soil creep. And the final one is a simulation without DCM and without soil creep. So here are the results. So if we look at the excess port pressure, so we can see if the DCM column was used, so the excess port pressure can be largely reduced. And if we consider the creep, so you can see here there was increase in the excess port pressure. If we look at the stress strain path, so we can see that if we use the DCM method for the Hong Kong marine clay, so you can see the point 1 is actually the simulation without DCM, and the point 2 is the simulation we conduct with DCM. So as we can see here, after consider DCM, so this looks like an unloading process. So from point A to from point 1 to point 2. So this unloading process, as we discussed before, is caused by load transfer. So this load transfer will take soil to an over-consolidated state. And if we compare point 1 and point 2, so the stress point at point 2 will have a smaller creep rate compared to point 1. So in this case, the creep deformation is therefore reduced. So we can draw the conclusion that the creep behavior of HKMD can be reduced by using a DCM method. So, and on top of this, so we can say that for the Hong Kong marine clay under the Hong Kong International Airport, so using DCM method is a good way to reduce the settlement and reduce the creep behavior of the soil. And now we need to think about, is DCM always a good method? So now we are more concerned about the cost of the DCM and also the environmental impact. For example, so in the conventional DCM method, we need to use cement as the binder material. So here we summarize some information about the carbon dioxide emission and the energy used to produce cement, GGBS, and ISSA. So GGBS and ISSA are so-called byproducts or waste materials from, for example, GGBS is from steel industry and ISSA is from wastewater treatment. So as you can see here, so if we want to generate 1 ton of cement, we actually generate almost 1 ton of carbon dioxide. So in this case, we don't consider cement as a green material. So so in next step, so we may try to consider, can we replace cement or partially replace cement with some more greener or sustainable binders to reduce the cost of the DCM, deep cement mixing method. And here we have the preliminary cost comparison. So as you can see here, so using the prefabricated band drain method is comparatively cheaper than using DCM method. So this cost comparison can be found in this research report. So you may scan this QR code to download this report for more information. And apart from that, we also have a YouTube video to introduce you the sustainable land reclamation approach proposed by Professor Yin. So you can simply scan this QR code to watch this YouTube video. And in summary of today's webinar, the post-construction settlement of HKMD can be controlled by using vertical drain and surcharge preloading method. A sustainable land reclamation approach using dredged HKMD as fill material treated by a combined ground improvement method using horizontal drain and vertical drain with vacuum preloading has been demonstrated by laboratory experiment and a field trial. Reducing the vertical spacing is more effective than reducing the horizontal spacing in enhancing the performance of horizontal drains. And the creep behavior of HKMD can be reduced by using DCM method. And the unloading process caused by load transfer takes the soil to an over-consolidated state with a lower creep strain rate. And lastly, sustainable binders might be used to replace or partially replace cement in deep mixing methods to reduce both cost and carbon dioxide mixing. And I would like to thank this opportunity provided by the Hong Kong IE Civil Division and Department of CE, and also my PhD supervisor and my colleagues. And also I would like to thank CEDD and AECOM and also Build Kim and Samsung for their support during the field trial. And here are the references. And also today's research presented in this webinar can be found in the following research paper. So if you are interested in, so you can download this paper to know more about the Hong Kong marine deposit treated by prefabricated band drains and deep cement mixing method. And thank you so much for attending today's webinar.
Thank you, Dr. Wu, for your insightful presentation. So now we will have the Q&A session. And let's see if we got some questions from the audience in the Q&A box. So I see there's a question about whether the presentation material can be shared with the audience later. Maybe we can share with the PolyU later. Yeah.
Oh yeah, I think I will send you my webinar slide, and then maybe you can help me to circulate the slides to the audience.
Okay, thank you.
Thank you.
Okay, so I see no more questions from the audience now. So yeah, thank you all for participating in this webinar, and the CVD certificate will be issued around 3 weeks after the seminar. Thank you very much for your time, and have a good evening. Thank you, Dr. Wu as well.
Thank you.
Thank you.
Thank you so much.
Bye-bye.
Bye-bye.